Here's the pitchfork bifurcation diagram that we just saw, where we start with one stable state and we branch to three states. Two of them are stable, one of them is unstable. This is also a bifurcation diagram for a supercritical pitchfork. Again, one stable state. Again, when we go to three states, two of them are stable, one of them is unstable. In addition to the supercritical pitchfork bifurcation, there's a type of bifurcation called a subcritical pitchfork bifurcation. It's going to be quite similar, but just a little bit different. Let's see what happens when we switch the sign of the cubic term. That's going to take us from a supercritical pitchfork bifurcation to a subcritical pitchfork bifurcation. And right now we're going to take a look at how the bifurcation diagram changes when the sign of that cubic term changes. Near the origin, x cubed is quite small, and so the behavior of f is really being determined by rx. So near the origin, for r less than 0, we'll have a negative slope right at the origin. And near the origin, for r equal to 0, we'll come through kind of tangent to the x-axis. And then near the origin, for r greater than 0, we'll come through the origin with a positive slope. Far from the origin, when this was minus x cubed, we had kind of a negative cubic thing going on, but now we have a positive cubic thing going on far from the origin. And then I just kind of connect up what's happening far away from the origin with what's happening right at the origin to get these graphs. Once I have the graphs, I can go ahead and draw in my fixed points, and I can identify their stability. Now it's time to construct the bifurcation diagram. I've actually already constructed it. When r is positive, the origin is unstable. When r is negative, it's stable. This is the same as our supercritical example. The origin was stable down here and unstable up here. What's different now is that previously, when we had a minus sign, the new states were born in this direction and they were born stable. Now, with the plus sign, the new states are being born in this direction and they're being born unstable. When these new states are unstable, we call the bifurcation subcritical. Just as for the supercritical bifurcation, the subcritical pitchfork can open in either direction. So stable to unstable or stable to unstable. The thing that makes it subcritical is that the extra states, when they are born unstable. I'm going to talk through these bifurcation diagrams using loading on a beam as an example. Think of the x value as the deviation of the center point of the beam from a vertical center line. Here in the supercritical bifurcation diagram, think of r, actually in both bifurcation diagrams, think of r as giving us the load on the beam. When r is small, the beam prefers to be straight. That's its stable position. When the load goes up a little bit, straight is still the stable position. When we pass through the bifurcation point, the load has gotten large enough that straight has become unstable, and instead the beam buckles to one side or the other, so the deviation is to the left or to the right, and the beam no longer passes straight through the center line. As we increase the load, the beam bends a little bit more. So that's the supercritical picture. The beam started straight, and it bends a little bit in one direction or the other. Now let's look at the subcritical picture. Again, let's start on this stable zero displacement line. So the beam is vertical, and it has some load. With an increase in the load, the beam stays vertical. Once we pass through the bifurcation point, under this model, there's not an obvious nearby stable state, and instead, the displacement is increasing without bound or decreasing without bound. Now, that would be unphysical. In the context of our model, let's just interpret that as collapse. The beam has bent or buckled and has basically crumpled and entered a different state where our model no longer applies. So in the supercritical picture, we started with a straight beam and the beam bent a little bit as the load increased. In the subcritical picture, we started with a straight beam And then the state of the beam changed very rapidly and moved quite far from that straight position.